Welcome to Aerial Services Ortho and LiDAR Accuracy, webinar number 2 of 3 in the Aerial Services Summer Webinar Series. This is your host, Joshua McNary, Marketing Manager at Aerial Services. We are pleased you have joined us and hope you walk away having learned about how Ortho and LiDAR Accuracy can be improved for your geospatial projects. But first, a few housekeeping notes. You may ask questions via the questions pane on your screen. We'll collect these questions for your response from our speakers at the end of the presentation. We want your feedback. Contact us via the chat pane or the post-webinar survey with any ideas, questions, or concerns regarding this webinar. The post-webinar survey will appear on your screen after you leave the session. Please use that as an opportunity to share your feedback. Lastly, but not least, note that Aerial Services will have one more webinar as part of our summer series. UAV and geospatial will take place on August 22nd. Please join us. Visit www.aerialservicesinc.com/webinars for more information and to register. I'm now pleased to introduce my colleagues and friends, Aerial Services President and CEO, Mike Tully, and Spatial Information Solutions, the makers of Accuracy Analyst and Topo Analyst, President and CEO, Chuck O'Hara, whom will share their expert knowledge with you today. Chuck and Mike have been on a mission in the last year to help educate geospatial users about the do's and don'ts of using accurate or inaccurate geodata. They spoke together on this topic at last spring's ASPRS annual conference in Sacramento and are scheduled to do a follow-up session at this fall's joint ASPRS/MAPS 2012 specialty conference in Tampa. Their insights into procuring and checking geospatial data to ensure accurate solutions and analysis has packed sessions in the past, and today's webinar attendance is continued proof of the relevancy of these topics. So with that, I'm happy to turn the session over to my friends Mike and Chuck, who will get on with the show. Mike, will you lead us off?
Sure, thanks Josh. Thank you everybody for joining us today. So let me ask you, if I was to put you all against the back wall and begin throwing darts at you, would you rather that I be imprecise or inaccurate? It's an interesting question, and I'm not going to answer it right now, but we'll talk about that and a lot of other aspects of accuracy today in just a bit. Next slide. Unless you're from Texas, you probably noticed something wrong with this map, and we've all seen them, bad maps. There's this one or the next slide. Labeling might be a problem. Scale might be a problem. Next slide. Sometimes it's just the underlying data that causes a problem, like this DIM that was used to create an ortho, or the next slide. Another common type of problem with underlying data that we see commonly in geospatial products. Next slide. Sometimes our vectors don't line up. And when this happens, what do? Or can you tell if the roads, the vector roads are bad, or is the ortho bad? And how do you know which data set is inaccurate? There could be a problem with projections. Maybe a transformation was a problem. Maybe the vector roads are bad. You just don't know unless you know more about accuracy. So today, next slide, what we'd like you to take away from this is why you should care about the accuracy of your geospatial data sets. Today we find ourselves, awash with free or inexpensive geospatial data, orthos and LiDAR, even iPad apps. The amount of data available for use in our geospatial applications and projects is going to continue to explode well into the future. And if you don't have a professional understanding of and care about accuracy, you may harm yourself or others with that data. Next slide. We're all professionals, and we don't ever want this said about us. Next slide, Josh. Yeah, thank you. So we don't want this said about us. So, what do we mean by accurate? How do I know how accurate my geospatial data is? How accurate is accurate? We want to talk about those things today. Next slide. The professional use of geospatial data starts with metadata. You can't know the accuracy of a data set without first having its metadata. It is not uncommon for us and Chuck, when we visit clients using geospatial data, that they don't have any knowledge of the metadata associated with the data sets they're using. They don't know where it originated. They don't know who created it. They don't know how it was created. And they often don't know why it was created. And metadata, properly structured metadata, hopefully FGDC compliant metadata, answers all of those types of questions and is where you start understanding accuracy. Next slide. One of the things, hopefully, that you'll find in good metadata is a description about the intended use of that data. A professional should be very concerned about the intended use of a geospatial data set because of the threat to public welfare and safety if that data is used improperly. Data is not to be used for some things, for some applications. For example, using 2009 Tiger data, road centerline data, that has a 25-foot horizontal accuracy, or that guarantees 25-foot horizontal accuracy. If you use that to align your property boundaries to, you may not have a good idea if you're expecting similar ortho accuracies in the range of 12 inches. So, in fact, if you've ever looked, the metadata for Tiger data says, quote, no warranty expressed or implied is made with regard to the accuracy of the data in the Tiger shapefile, and no liability is assumed as to the positional or attribute accuracy of the data. So know what the intended use of the data is, because you can very easily misuse it and think it's more accurate than it is or was ever intended to be. What's the positional accuracy of Google Earth? If you look, you'll find that there is no accuracy defined on their Wikipedia page, and it's left up to as an unknown. So maps are created for a reason. They can be used for some purposes, but not all of them. So be very careful and understand their intended use. Next slide. Speaking of accuracy, another common misconception in the GIS community that we run into a lot is that accuracy can be inferred by GSD, or the pixel size. Or when we're talking about LiDAR, people assume that LiDAR is more accurate with more points on the ground than less. And I want to use this picture here to illustrate how this assumption is flatly untrue. There is no direct relationship between resolution and accuracy. So on the left here is a picture. The same picture is on the right. The picture on the left is high resolution. It's broke into 36 pixels. So it's high res, 36 pixels. The one on the right is just 4 pixels. So low res. Got a very big GSD. Because both pictures are from the same ortho, they all have the exact same accuracy. The higher resolution on the left is no more accurate than the low resolution. There's no direct relationship between accuracy and resolution. I could likewise show you LiDAR data that has a high point count per square meter and others that with a low point count. You cannot infer accuracy based on the density of LiDAR on the ground. Again, you'll discover this kind of information in well-written metadata. It's important to understand this. Next slide, Josh. So let's get more technical here for a minute and discuss error and accuracy. Anytime we measure something, no matter how careful we are, no matter what tools we use, that measurement has error. There's no way to escape it. A variety of factors contribute to that error, and what this graph is showing us is that of all the error, that total error budget, most of it is systematic error. And a very small part of it is random error, bias error. Systematic error we can do something about. We can more carefully measure. We can use better instruments. We can model away error in systematic error. The random error, the bias error is a different type of error that really is just inherent in the instrument we use, and we really can't model it out, and it's just a part of measurement. So for example, if, down below, we exploded that systematic error to show that in a typical remote sensing application, whether it's LiDAR or a camera, there's basically 4 types of error that make up systematic error. Again, error that we can do something about. By far the biggest source of error in our remote sense data would be position or GPS data and attitude, which way the sensor is pointing. Other types of error would include instrument error, errors associated with the camera itself, the lens inside the camera, the mirror inside the laser, things like that. Data processing is another source of error. We can introduce error just by the way we process data, the software we use, the projection we apply, the transformations, the tonal adjustments that we might make. And then lastly, human interpretation of the data. We might classify things wrong. We might make mistakes in the way we identify which features. Operator training, poor operating training can influence error in that respect. So it's the photogrammetrists or the remote sensing experts' responsibility to understand these sources of error and manage them responsibly. We're going to do that with our training, with designing the project, with knowledge about the parameters and such to control or reduce the errors that are possible given the project restraints. Next slide, Josh. From the error sources, we move on to the standards, the accuracy standards of measuring and reporting error. This is a list of the different standards we've all, most of us have heard of. By far today, the NSSDA is the predominant standard in use. And this is how, as you acquire or produce geospatial data, this is how positional accuracy should be defined for digital mapping data. Older standards that are still used, some are ASPRS and National Map Accuracy Standards. And of course there are other organizations that have their own standards like FEMA, NOAA, the U.S. Corps of Engineers. They might have other standards unique to them. We'll learn here in a little bit that ASPRS is coming out with some new revised standards that may actually replace or supplement NSSDA. But for now, NSDA is the most logical standard to use for geospatial data. They're important because when used properly, they objectively quantify and report the positional accuracy of a data set. And this is important because it helps us compare one data set with another. If the same standard is used to measure and report a data set, then you can compare those two data sets with each other. And good metadata will report if the data set was tested for accuracy and to what accuracy standard it was tested to. So with that, I'm going to turn the rest over to Chuck. Chuck, take it away.
Thank you so much, Mike. Next slide, please. So when we're talking about accuracy or uncertainty, it's important that we understand certain concepts that include accuracy, and that's quantifiable accuracy, versus uncertainty, which is not quantified, but it's a lack of knowledge about the characteristics of the data. And when we're talking about accuracy, we're talking about things such as precision, the completeness of data, the correctness of data, the consistency of data, the currency of the data, meaning how up to date it is, the lineage of it, meaning how it was acquired, processed, and what modifications or transformations have been made to it, and other factors that can influence the accuracy and the quality of the data. Next slide, please. So when we're looking at geospatial data, methods that we use to know whether the data are good include visual inspection, or what we would call subjective or qualitative evaluation. The evaluation of independent experts, meaning having subject matter experts that come in independent of the production team or of the customer to help advise as to the quality and the accuracy of the data. The use of demonstrated methods that assure that the data are being produced in methods that in the past have been demonstrated to deliver data that meet the accuracy specifications and requirements, and the ability to deliver, verify, and report the accuracy of the results. Those are things that help us to ascertain whether or not the data are good enough or they're fit for use. Next slide, please. So when it does count, the things that we're concerned with are measurement accuracy, meaning how are we looking at photo identifiable locations, survey checkpoint locations, and how do we compare that to locations or to positional information in the geospatial data. The opinion of experts, the use of independent firms to provide services that help us to verify the data or to collect survey checkpoints or control, or to go out and collect land use or land cover information, and the use of standard and verifiable methods in a consistent and objective manner for the project. Those are all important factors to consider when accuracy counts. Next slide, please. So in doing this in practice, many of the standards, guidelines, and specifications that have been in use, or those that are new and evolving, refer back to primary references, such as the often cited works of Greenwald and Schultz back in 1962. So whether we're looking at standards from the National Standards for Spatial Data Accuracy and SSDA, or whether we're looking at the new standards being published by USGS that we are referring to as the version 13 specification for LiDAR guidelines and base specification, or whether we're looking at references such as Congleton and Green's work on assessing the accuracy of remotely sensed data. Most of these standards refer back to earlier works that deal with the quantification of accuracy, error, and uncertainty. And as our data evolve, the producer and end-user communities of practitioners are seeing greater emphasis, as Mike said earlier, on high-resolution products. But the capabilities to quantify data as having high accuracy or high quality are based on standard methods and governing accuracy equations. Next slide, please. So as we're taking these standards and reducing them to application, we're faced with reducing accuracy standards to fundamental governing equations and to providing methods that automate the input of the data to be tested, methods to automate input of reference data comprising precisely surveyed checkpoints, and quantification of checkpoint error. And when we're quantifying checkpoint error, that's used to compute products such as the mean error, standardized error, which is also commonly referred to as standard deviation, the root mean square error in X, Y, and Z, as well as the National Standards for Spatial Data Accuracy, which typically computes the 95% confidence level. And that's used for both horizontal accuracy, accuracy R, as well as the vertical accuracy, accuracy Z. And we often see that referred to as the 95% confidence level in SSDA accuracy. So one other thing to be aware of is that when we're looking at RMSE, the value of the checkpoint data is typically acquired at an accuracy that's 3 times the accuracy of the required accuracy of the verified product. So if we're looking at data that have a requirement for 3-inch accuracy, we would have to be surveying data with a precision of 1 inch or better in accuracy. Next slide, please.
Chuck, can I add something there?
Absolutely, Mike.
Yeah, I just wanted to say that those formulas look daunting to the to some people, but these are standard statistical formulas that are used to measure error and assess error in almost any application you can imagine. It's not just geospatial. So don't let the formulas scare you. They're very standard. There's nothing unique here to geospatial. These are just standard statistical formulas for error.
Right, and it's the challenge of the practitioner to basically eliminate the complexity by making a user-friendly application that allows the data to be input, the checkpoints to be input, and the checkpoint offsets to be extracted automatically, allowing the equations to be performed behind the scenes transparently in a very consistent and easily followed manner. So those governing equations are behind the scenes in a well-defined and delivered application that automates the QA process. So having said that, the existing standards that we're accustomed to now might be supplemented or replaced by next generation accuracy standards. So we're in this age when we have data resolution from new digital sensors that are providing data of unprecedented resolution, and along with that, positioning and georeferencing technologies deliver the capability to process and deliver data of extraordinary accuracy. So along with these capabilities for higher resolution and accuracy, there's a need for next generation definitions and standards that define classes for data of higher accuracy. So to meet this need, we see new accuracy standards emerge for digital geospatial data from organizations like ASPRS. For these new data, there may be accuracy definitions for standard high accuracy, lower accuracy, and extra high accuracy. And in the examples that follow, Class A products refer to standard high accuracy data, Class B refers to lower accuracy geospatial data, and Class X products refer to extra high accuracy geospatial data that might be suitable for the most demanding user applications. And I want to note that these are shown as examples, and the actual final standards that get published by ASPRS might vary somewhat from what you're going to see in these next slides. Next slide, please. So here we see ortho imagery horizontal accuracy standards. These standards attempt to crosswalk the classless or scaleless image resolutions to NSSDA specifications for a particular class of data accuracy and to extend that to an equivalent national map accuracy standard specification and to appropriate map scale use. Now, currently, as Mike said earlier, the NSSDA standards are scaleless. But here we attempt to specify RMSE and 95% confidence levels and to crosswalk those to scales for appropriate use of the data. So in this table, we can see that accuracy class A has a root mean square error that's equal to 1.5 times the pixel size. Class B, in which root mean square error is 2 times the pixel size, and accuracy class X has an RMSE equal to the pixel size. So if we look at class 1X, or class 1 extra high accuracy, which is the top row, we can see a pixel size of 3 inches, RMSE and X or Y of 3 inches, and an RMSER of 4.2 inches, and NSSD accuracy of 7.3 inches. We see the equivalent CMAS 90% confidence level and the appropriate scale, and a new item that we see is the mosaic seam line maximum mismatch of 6 inches. That's a seam line mismatch of 2 pixels. That's pretty high accuracy, and we'll need some pretty nice tools to be able to verify in QA that data can meet these kind of standards. Next slide, please. Similarly, for LiDAR, we see standards in which point density, RMSE, and Z, fundamental vertical accuracy with the 95% confidence level, consolidated vertical accuracy at the 95th percentile, and equivalent NMAS specifications and relative accuracy in the swath overlap are defined. Here, we see that class 2A, which is in the middle and highlighted, equates to the current USGS version 13 specification, in which we see a 1 meter pulses per square meter, 12.5 centimeters RMSE in the Z, and the associated fundamental vertical accuracy and consolidated vertical accuracies that comply with the current USDA spec. Note here that the relative accuracy in the swath overlap is cited as an RMSD value. Now, the difference between RMSD and RMSE is important to note. RMSE, as we specified earlier, is an accuracy that's computed from a reference that's 3 times more accurate than the governing accuracy requirement for the data set. Here, RMSD is root mean squared difference, and this is a difference in values computed between 2 data sets that are expected to have similar accuracy. So this is an important new change that might be inserted into accuracy specifications for LiDAR data. Now, if we look at this data, all of these columns, except for the column 2 and the final column, would also apply to digital elevation data compiled from stereo photogrammetry. So if we want to look at new data that are being acquired, in some areas, such as in the Pacific Northwest, data are being acquired that might meet class 1X, or 8 pulses per square meter, RMSE in the Z of 9.2, and swath accuracy in the overlap of 6 centimeters. Next slide, please. So we're moving into this era of higher resolution and current data that have to be maintained. We're seeing a change in ortho resolutions from 1 meter or lower resolution to 3-inch or 6-inch orthos. A lot of the times these data are being compiled or acquired by state, county, and local government. We're seeing LiDAR data that are being collected not at a 1 meter posting or 5 meter postings, but with pulse densities that approach or exceed 8 pulses per square meter. As we look to use data across regions, across states, or across the U.S., we have to look at whether we can simply blend the data together, or do we do national level reviews of data, specifications, and accuracy to understand which data can be combined into national or regional products. And the question becomes, how do we look at standard methods and test approaches and methods and metrics for making decisions about what data we can continue to use or can use for broad-scale or regional applications, as well as how do we evaluate the best available data for local applications? Next slide, please.
Chuck, I'll just add to that, too, that as we see this geospatial data becoming more and more dense, higher and higher accuracy, there's more and more LiDAR points. Instead of millions of points, there's billions. Instead of hundreds of photographs, there's thousands or hundreds of thousands. And how do you test the accuracy of a billion points or 100,000 photographs? It begs an application that facilitates measuring the accuracy of that volume, that great volume of data.
Right, and that goes to the issue of, do you just check part of the data and do you use your manual methods, or do you develop automated methods that will consistently and completely fully test the data? And that's where we're going to look at several points as we move through the remaining slides. But this slide positions the method for actually conducting checkpoint analysis that's used to measure positional accuracy. And here we have a reference coordinate shown in blue and an image photo-identified location shown in yellow. And from this we compute the offsets in X and Y to calculate the error offset or checkpoint error. And those terms are combined by taking the square and the square root of the sum of the squares to come up with the total radial offset of a given reference location to the image coordinate. So this is the method whereby we compare referenced and photo-interpreted locations in order to compute horizontal accuracy. Similarly, we have reference locations that compute a z-value, and in the vertical we compare that to the elevation from either the point cloud LiDAR data or to the DEM surface. And that's a z or z offset. Next slide, please. So as we take these checkpoints and we tabulate them for data collected across a study area, we're advised to collect 20 or more than 20 points in order to get a statistically rigorous sample set. And when we tabulate those data, accuracy statistics can be computed from the checkpoint offsets. We identify the photo locations and compute those differences in X and Y's, compute the accuracy statistics, and we use charts, graphs, and statistics to deliver understanding about the distribution, the magnitude, and the sources of error. Next slide, please. So as we're looking at this, when we look at the distribution of checkpoints across a study area, we can look at a circular error plot that shows the amount of X and Y error contributed by each point. And the top circular error graphic shows a series of points that all fall in the northwest quadrant and well out of the circular center of the target. This would indicate a data set with a large amount of systematic bias. And similarly, the plot that's to the right of that, or the vector offset plot, shows a series of vectors all pointing to the north and west away from the source of the point location for the error. So here we see a data set that has a large amount of systematic bias. When we remove that bias, we're left with error that may include other forms of data, other forms of error that can be removed. And the result is a small amount of error that's randomly distributed and has a near zero mean, and at that point we have what we would consider to be good data. So this shows how the circular error plots, vector offset plots, and statistics can combine to give us understanding of, have we removed bias, have we addressed error, and are we delivering data that meet the accuracy requirements and specification. Next slide, please. So again, this gets back to the slide that Mike presented earlier, in which systematic error comprised the largest portion of the error budget, we can eliminate or address as much as possible of that in calibrating the data, getting our positioning information correct, addressing any instrument issues, calibration, doing correct data processing, making sure that our projection and datum information are correct, and our interpretation or the rules and the transforms that we apply to the data are done consistently and appropriately. And after we've done that, we've eliminated as much as we can from the error budget, and there's always going to be a certain amount of random error that's left. But reducing that to the minimum amount possible is all part of the process of creating highly accurate and high-quality data. Next slide, please. So as we're measuring checkpoint error and accuracy, we get to this concept of absolute accuracy and relative accuracy. Absolute accuracy, as we've said, is computed by comparing surveyed checkpoint locations that are 3 times the accuracy of the required accuracy of the data set to points that are located in the data set or to photo ID locations. So this is highly accurate reference compared to position locations in the data set. When we're looking at relative accuracy, we're looking at the location of the feature in a reference image data set compared to the location of the same feature in a test image data set. For the absolute accuracy, we're computing root mean square error. For the relative accuracy, we're really computing a root mean square difference product. So this goes back to this RMSD concept that was earlier pointed out in this next generation accuracy standards or criteria that we'll be seeing in the future. Next slide, please. When we're looking at checkpoint error and accuracy, whether it's absolute or relative for different sensor systems, we may have situations where we have rotary-mounted or helicopter-based LiDAR and ortho acquisition, as well as on fixed-wing craft, in which we're collecting or co-collecting optical or aerial imagery, as well as LiDAR data. We can use absolute accuracy methods or checkpoints to compute the horizontal accuracy of both products. We can also look at the same locations in both to cross-check the data to assure that they're correctly co-registered. So we can evaluate absolute accuracy as well as relative accuracy, both between image types collected over time or with different resolutions or different spectral bands, or in this case, different sensor platforms. We're looking at imagery versus LiDAR intensity data. Next slide, please. As we evaluate LiDAR and digital elevation model absolute accuracy, more and more often what we're seeing are tiled data and data checks for consistency and completeness of the delivery, and an abundance of checkpoints collected over multiple land cover types. In this particular application, there are approximately 15 counties of data and as many as 5 land cover types, and in each county a requirement to collect 20 checkpoints per land cover type. So we may have over 800 points. And in this particular case, we're looking at the bare earth land cover type, and we have 271 observations for that. The accuracy statistics that we would typically collect for those would include minimum, delta Z, maximum, mean, number of observations, and the standard deviation, as well as root mean square error in the Z. Now, since we're evaluating this for the bare earth category, this is the fundamental vertical accuracy, and we apply the 95% confidence level and compute a Z value, which is 1.96 times RMS EZ, or a value of 13.7 or 13.7 centimeters in this case. Next slide, please. On the previous slide, what we saw were the final deliverable products and accuracy checks performed on those. But as we're looking at the LiDAR life cycle, we have to look at it as life cycle products. And if we don't check, verify, and address issues in different phases of the project, then it's very likely that the data will fail at the end. So as we're doing acquisition, calibration, and final products, it's important that we perform checks along the way. In the acquisition phase, we're certainly interested in completeness of coverage, adequacy of spacing, density, the consistency of the observations, the amount of overlap in the data, again, the coverage, and in every step, we're looking at the LAS compliance. Once we've calibrated the swath data, we're still looking at the completeness, the LAS compliance, the degree to which the data calibration has delivered a relative accuracy that meets the requirement for relative accuracy in the swath overlap, and again, the coverage. Once we get to the final products of the classified and tiled data, we're looking at the absolute accuracy of the DIM and the LAS data, the degree to which the data have been correctly hydroflattened, the presence of break lines, as well as water body outlines, the metadata that are to accompany the data, and any LiDAR accuracy and surveying reports that are required to be provided along with the deliverables. Next slide, please. So as we're looking at verification across the life cycle, it's important that we have tools where we can efficiently and consistently look at the coverage of the LiDAR swath data. Are we getting complete coverage, or do our flat lines include voids or areas where we are missing or have gaps between our overflights? If we have a requirement that there be 20% overlap, do we have methods to efficiently verify that? And in looking at the coverage as well as overlaps, do we have methods to efficiently determine if there are holes or voids in the data? And if there are those due to water bodies, which are allowable holes, or are those holes or voids due to system outages or holidays in the system collection? It's important that we have methods where we can rapidly and efficiently determine coverage, overlaps, and holes or voids. Next slide, please. So as we look at that, when we're evaluating coverage, it's also important that we can count or evaluate the density and the spacing of the data. According to the USGS version 13 draft specification, there's a requirement for coverage and spatial distribution that we have a pulse count grid that's created at a nominal pulse spacing times 2, and we have at least one pulse count in at least 90% of the cells that are created. That's a threshold that we can use to determine pass or fail on density and spatial distribution, and there is a need to be able to efficiently create raster pulse count density grids. Well, but when we combine that with our holes data set and our coverage, what we find is the ability to use those in overlap and be able to efficiently determine whether or not any gaps in the data are due to water or if they're holes. And this also can help us to begin to get a head start on creating or compiling our hydro break lines and looking at areas where we would expect water bodies to be in compiling and preparing our data for review and for preparation of hydroflattened DEMs. Next slide, please. As we look at the data as we move into the second phase, which is evaluating the calibration, it's important that we understand that properly calibrated and adjusted swath data should result in high relative accuracy between the swaths. Now, even if we meet the requirement to produce data that are better than 10 centimeters in root mean square error between the swaths, there's still the possibility that there could be visible step errors, and if we compute hill-shaded LiDAR swath data and we look at those, we shouldn't be able to really see detectable step errors between LiDAR swaths. So properly calibrated data, such as are shown on the right, would eliminate visible step errors between the LiDAR swaths as shown, and would eliminate any kind of patchwork quilting also between the data sets. Next slide, please. As we look at LiDAR relative accuracy or error testing, we evaluate the swath overlap, and there are many methods that are being used to test this. In this case, we're subdividing the overlap into a number of segments, extracting the Z values from both LAS files, and computing the differences in Z values. And here again, we're computing an RMSD in Z for relative accuracy statistics. Common methods that are also in use include looking at Z difference rasters, which are images that compute the difference between the LiDAR elevations and are used to show visuals that depict the differences in increasing shades of green or red for increasing offset between the two different LiDAR data sets. So here on the right side, we can see a root mean square error in Z of 7.78. That's better than the 10 centimeters that are required for pass-fail of relative accuracy in the LiDAR data. Next slide, please. So it's important, I guess, for us to look at a high level of what's important to test in the phases of the LiDAR lifecycle. In phase 1, where we're looking at uncalibrated data, we're looking at coverage, completeness, correctness, consistency, gaps, and density, and those are primarily conducted on the producer side to answer the question, am I done flying? If those data are also delivered to the customer can evaluate the data and say, were these data collected correctly, completely, and consistently to give me the data I need? In phase 2, we're looking at calibrated data and evaluating whether the data meets spec. In phase 3, we're looking at whether the data meets specs and are ready for delivery. Next slide, please. Over and above quantitative accuracy verification, there are advanced visual metrics. And these are metrics that are being used in large part by most folks that are doing quality assurance now. And here we're looking at whether we can see artifacts from the tin data in our hydroflattening. We're also able to see errors in the stream where there's not a monotonic increase in the elevation or a smooth surface for the stream water body. We also can see things like spikes or pits, as well as improper bridge removal from the DEM product. These are typically advanced visual metrics that are performed, and this shows the raster data, but we can also look at things like whether or not brake lines float above or they are below the point cloud data if we're looking at the LiDAR point cloud in 3D as well as 3D brake lines. Next slide, please. So now we get to the question of who's doing the work, and increasingly we're seeing a situation where there are federal, state, and local partnerships. In those cases, we have blended requirements for verification, and that presents challenges to whoever is doing the verification. And what we want to ensure is that we're not just sacrificing quality assurance just to get more data. In truth, whether we have the case that we're rounding up the usual suspects to the best vendors, even in those cases, we need new methods to automate verification. And new tools and methods are certainly needed to reduce the cost and increase the efficiency to fully verify and audit new data. And at the bottom, you know, the thing that's trying to show is that if you only have a hammer, everything ends up looking like a nail. And the reality is that we probably need more tools that can address how we can verify and assure the quality of next generation data. Next slide, please. So in reality, the status quo is that almost all companies that are producing the data have accuracy and quality tests. There is no easy button to this. There is no single tool that does it all. It's a complex combination of tools and methods. The good news is that there are standards and working groups that are providing advanced science, technology, and guidelines that can help us to assure the data to meet next generation requirements. And certainly in all cases within companies, there are existing internal or homegrown solutions, scripts, tools, and methods that are manual and in many cases automated tests. And certainly there are internal versus commercial off-the-shelf solutions that are evolving to provide industry standard practices. Next slide, please. if we're looking at internal versus commercial methods, there's a possibility that the internal methods may have some bias to their production methods, whereas the commercial methods may be independent of any sensor system or production capabilities. Internal tools can become outdated and legacy, whereas we would hope that the commercial tools provide new capabilities and are current. Certainly, internal tools are self-supported, and that means that you have to keep them, and whoever's using that or providing that tool supported internally, whereas with commercial tools, they're provided support provided externally. With internal tools, you just have internal users as opposed to commercial tools with communities of users, and internal tools are expensive to develop and maintain, whereas external tools may be purchased and maintained. Internal tools, there's manual processing. External tools, automated. If you have a large project in which there are multiple partners and participants, if everyone has their own tools, you can have inconsistency in results. If everyone's using the same methods, you would expect to have consistent results. Internal tools are not easily shared, whereas commercial tools, the products, the tools, and the methods are more easily shared. So this is just some pros and cons and some comparisons between internal versus COTS tools for auditing data. And as we look at the geodata status quo, next slide, please. We see a situation where we have multi-generation map products, both in ortho as well as LiDAR data, where acquisitions have been conducted over time with different contracts, different data, and different vendors, and different verification vendors. We have different specifications and different verification approaches. And the symptoms of that may become a reality that we have to deal with is that the data can become more of a patchwork quilt of resolution, sources, and accuracies. Reacquisition may become a major trend, and there may be too much data to just manually check. The reality is that if we can't check them all or manually verify them, that may mean that we become prone to saying we're going to check 20% of the tiles. And what this means is that we may miss major fatal flaws in the data. And it may also mean that we lack consistent methods and approaches that are applied uniformly across the data sets. These are symptoms and issues that we have to be cognizant of as we produce and use data. Next slide, please. And here I believe is where I turn it back over to Mike to address where best practices are needed and to discuss briefly what those are and how they vary.
Okay. We certainly need better tools, and we see them being developed by folks like Chuck and Spatial Information Systems solutions. But things like density, the density of points on the ground, coverage, consistent coverage across the project area, overlap, whether it's orthos or LiDAR data, has to be consistent and within spec. Sensors need to be calibrated typically before each mission to ensure that all the different components in a camera or LiDAR system, and there are many, are all working optimally and aligned precisely. Brake lines. Best practices are things like consistent digitizing of brake lines, complete digitizing of features as brake lines, etc. The current methods are numerous. Every project will have different specifications for spacing and accuracy, and it's important that the provider and the client understand what specifically these specifications are and how to best design the acquisition and the delivery of the products to meet all of those specifications. Next slide, please. With that, we're finished with the presentation and are happy to address any questions. And I'm going to turn this over to Josh to lead us through that phase.
Yes, thanks, Mike and Chuck. Great presentation, very informative and very useful information. So I hope our audience shares that sentiment. Thanks for sharing your knowledge with us. So now on to the questions from our attendees. We already have some coming in. Appreciate those. We do want to note that we want to stay away from being overly project-specific with the Q&A. So if you have any project-specific type questions, you can feel free to add them here, but we will have to get back to you after the event on those if there's anything really specific. But generalized questions, feel free to add them now. You can also feel free to call us anytime after this event ends here at Aero Services or with SIS and discuss LiDAR ortho accuracy issues, even if it's just general questions and you just want to vet those further, even if you don't have specific projects that you are going to request of us. So with that, again, feel free to add questions as we go on here. And I'm going to ask one that came in from Adam I'll have both of you address this if you're so willing. The question is with regards to the pixel mismatch that was discussed earlier on ortho photos. Is that applicable only to the ground, or can it also apply to above ground objects like transmission line catenaries and other above ground features? How does accuracy apply to that, specifically with regards to orthos?
Josh, I missed the middle part of that question. Can you repeat that one more time?
Sure. The question was with regards to pixel mismatch in orthos. Does that apply to the ground only, or can it also apply to above ground objects like transmission lines, etc.?
Oh, sure, yeah. Absolutely. A pixel mismatch can apply to any feature in the ortho, whether it's the ground or a tower or a building or bridge. So yes, it can apply to any feature visible in the orthos.
Let me add to that. If he's referring to the next generation specification for the seam line mismatch in the pixel for the different next generation classes 1, 2, and 3, A, B, and X, then I'm not certain how they're going to apply that. But what that stated is the maximum mismatch along the seam line. So if the seam line for the ortho data cuts through or truncates a feature that's above ground, I would have to think that would be part of the error criteria and looking at how well they match. There may be some leeway in whether it's a road feature or an above ground feature, but I think that's part of these new standards that's going to have to be ironed out.
Yeah, he was addressing the seam line mismatch specifically. That's what he was asking. So thanks there, Chuck. Okay,
yeah, so,
Dana. I'm sorry. Go ahead, Mike.
Well, I was just going to add to that. So if he was talking about the mosaic seam line mismatch, then yeah, the specifications will say that a mismatch of some proportion is acceptable, 1, 2 pixels, but beyond that, the feature should not mismatch, and it can apply to any feature, whether it's on the ground or not. Great.
All right, so Dan had a question with regards to, he asked, are there big differences between ASPRS and NSSDA standards? And also, with regards to the draft specifications with ASPRS that we showed, will it look like the slides that we noted, or that Chuck went through, with the different levels of accuracy? Is that the actual draft, or is that something that we came up with? I think is what he's implying. Chuck, you want to take that?
Sure, that is an actual copy of the draft. I want to say it's like version 6 of the draft. So yes, those tables were actually extracted from the draft digital geospatial data accuracy standards.
And we're going to try to provide some of that. I'm sorry. I was just going to say that we were going to try to provide some of that information and links and whatnot in the post-event emails to all of you that are attending and registered. So you'll have additional opportunity to look over all that.
So the first part of that question, Josh, was that how do the ASPRS versus the NSSDA specifications vary? Was that
he specifically asked, what are the big differences? Are there big differences between those two standards?
Well, ASPRS standards are typically based on the maximum RMSE in X, Y, or Z, and they would tie that to either a scale as well as in the vertical, a contour requirement such that the RMSE and Z for a particular contour interval would have to be 1/3 of that interval. So the ASPRS standards that we see are tied to scale, and they are related to RMSE, whereas NSSDA is computed from an RMSE product in a 95% confidence multiplier Z value.
Thanks, Chuck. We are, just a note to our attendees, we are at 3 o'clock, which was the original end time for this event. We do have a number of additional questions, so I think Mike and Chuck can hang on the line and answer those. So we'll just continue on. If you do have additional questions, go ahead and throw them out now so we can try to get them in before we end the session. So let's go on. Robert had a question. I'm going to read this word for word because he had a very specific question. When the distribution of accuracy check measurements don't approximate to the standard bell curve, the mathematical relationship constants between the RMSE and 95% confidence don't seem to hold true. Can you comment on this, and have you had any experience with this? Does that ring a bell with you, Chuck or Mike?
Chuck, why don't you start that question?
Sure. When let's say that we were looking at something where the errors are not either normally distributed or where the distribution is not circular, and where the deltas in X or Y predominate. In those cases, the error distribution is more elliptical, and in those cases, the RMSE in one or another direction may predominate. So, if we don't have a sufficient number of checkpoints, or two, if the errors are not normally distributed, we may see that the data either are grouped if it's systematic bias within certain areas in the circular plot, or they all point to in a certain systematic direction in the vector offset plot, or there just aren't sufficient points in order to get a data set. So we would see values that are non-zero mean, RMSE in X or Y that may predominate, or bias statistics that would give us indication that we don't have either sufficient checkpoints or that the data have some kind of bias.
And I might just add that we do see this. It does occur. These statistical measurements of error do make assumptions about a normal distribution of error around a mean, that they do assume that there's circular error and not elliptical error, that the error in X is about the same as the error in Y, for example, circular. So, but we do see cases where there is elliptical error. The error in X is more than the error in Y, for example. We do see data sets where the error is not normally distributed. In those cases, when we're using proper QA/QC tools and methods, we will observe that. We'll detect it. We can measure it. We can quantify this non-randomness, these non-circular errors, and then we can construct an approach to deal with it. We can either reassess how we collected control or measured checkpoints. maybe we didn't use randomly located points as checkpoints. Maybe we need to add more control points to the data set to eliminate some of the non-circular or non-random errors. Or sometimes because of the project constraints, there's nothing we can do except report it and indicate in the metadata to the client that this is what the result is, and here are the options.
I'm going to add to that really quickly. Robert, when we have a situation where it is non-circular, the FGDC or NSSDA or ASPRS guidelines all do point back to Greenwald and Schultz to some extent. But they're all simplified into two special cases. One in which RMSE X and Y are equal. That's case one. And then case two is when RMSE and X does not necessarily equal RMSE and Y. And they give two simplified equations. But if you go back to the original Greenwald and Schultz diagram, they have a series of values where they take the actually standard deviation in X and Y, and they compute ratios of the minimum to the maximum. And then they look at the relative values in those, and then they have linear combinations that are used to compute the error statistics based on the relative values of those. What we see in practice, though, is that the FGDC NSSDA guidelines have simplified that. So there are a lot of assumptions in how those are applied, but if you really want to dig into the governing accuracy equations, you can always go back to Greenwald and Schultz and look at how it would be more rigorously quantified. But in general practice, from professionally acquired data using best practices and methods, it's usually safe to use the governing equations and the simplified methods that are applied in NSSDA and ASPRS specifications and standards.
Thank you, guys. That was a very good answer. Thought out. Thank you for providing that for Robert.
Sure.
Okay, so the next question I have in the list here is someone was asking specifically a housekeeping item on will this presentation be available via audio after the conclusion. I'll take that since I'm the one that'll be preparing that. Yes, we will provide this session via video and audio is the intention via the Aero Services website, and all of our attendees and registrants of this will receive a link to that. We'll also attempt to provide the slides and the some other links and references to some of these certifications that we've talked about during the session today. So look for that, and hopefully as long as all of our post-production goes well, that'll happen soon. Next question was with regards to oblique imagery. Dan was asking what work has been done for testing the accuracy of oblique type imagery, 45-degree angle imagery that we've seen become popular over recent years. Mike, I know we've seen mixed results with that. Chuck, I'm not sure if you guys have ever done any work with regards to that type of imagery specifically.
I don't know is the short answer. I don't know how much rigorous research has been done to quantify air and oblique imagery. It's a good question. It's a whole different type of product because the scale is constantly variable. From the center of an oblique out to any edge, the scale is different. So the air is different. Chuck, have you got any experience with obliques?
I've only on the research side, we've looked at some of the tools and the methods of measuring elevations using oblique imagery. And as you say, depending on the feature, the scale, and the location, it can widely vary. We have not put a lot of effort into creating tools that automate those processes. Associated with the oblique, there are ortho deliverables that we've looked at and we've done some testing of, but nothing too in depth because we really haven't had a data set that's been compiled to meet or that it's been delivered to us to say check this using checkpoint analysis and verify the horizontal or positional accuracies. So there's really not been that much on our side of verification of oblique.
If there's anybody listening that knows of statistical methods or even standards for error in oblique photography, send them to Josh at the email address he provides, because I'd like to know it. I'm not sure that there are any standards for oblique imagery, again, because it's a different animal. It's an image, unlike an ortho that has constant scale, a fixed scale. An oblique has continuously variable scale, and therefore the error at any point in the photograph is different than the error associated with another point somewhere else in the photograph.
Okay, thanks, guys. Looks like we have one more question for sure here before we wrap up. How do you generate break lines? Vertical imagery, LiDAR stereo models, or 2D digitizing and the draping the LiDAR over that data set? Mike, I know we've got experience with this. Do you want to start off with that?
Sure. Basically, there's several methods. The best and most preferred method is to do it from stereo imagery. So with stereo imagery, you can see the features in the photographs in 3 dimensions, and you can very accurately see the bottom of a ditch or the top of a feature and digitize it in Z. A second method is to use LiDAR grammetry, where you have your LiDAR points available to you in stereo and can detect where the bottom of something is from the LiDAR points themselves or the top of the feature, and digitize that way. A third method is to digitize features from heads-up digitizing or from a 2D photograph. That's not as accurate. You don't have any 3D information, so you're digitizing the feature from the flat image and then laying that line over the top of another surface from a DEM to give it a third dimension. So stereo photos are the first and best method of digitizing break lines.
Well, great. If there are no other questions, I think we're going to wrap it up here. Appreciate the talk, Chuck and Mike. It's been great. Appreciated all the questions being answered on behalf of our attendees. And again, to our attendees, please note that we will be providing links following the event here within the next week with audio, video, slides, and other references to the what was discussed here. So thank you all for coming. Don't forget to fill out the survey as you leave. It will appear. And thank you again. We'll hope to see you again soon, perhaps at next month's UAV and Geospatial webinar, August 22nd. Thanks, everyone. Thanks, guys.
Thank you, Joshua. Thanks, Mike.